future. Okay, so just in general, and I think the notation just kind of throws people off as it's written there, but at the top there, the function and its inverse compose together. So not multiplication, but compose. So if you have inverses, if you take the function, this is f, and you put in, remember that little -1, that just stands for the inverse. So this says if I plug the inverse into the original function, that would be the same as if I reverse the order, if I put the original into the inverse, and not multiplication, we're going to literally plug them in. And both of those should simplify to just give you x. And that's what we're going to be looking for as we go through these problems today, that once we plug in and do the algebra, it should all just simplify down to give you back x. Now, you actually have to do 2. So it says how to prove functions are inverses of each other. You're going to compose the function, like the original function, and its inverse, and then you're going to compose the inverse and the function. So we're going to it's going to look really similar, but it's reversing the order. So you're going to plug the inverse into the function, and then we're going to plug the function into the inverse. It doesn't matter which one you do first, but you have to do both and show that these both will simplify to be x. So these are kind of like 2 problems in one. And I'm just going to do with you guys some of the different types of equations that we had. And my first one here, this is just f of x is 3x minus 15. This is just a line. And a lot of people might not know this to look at this next equation the way it's written. I'm going to leave it like it is here. This is actually the equation of a line. It says x plus 15 over 3. I'm not going to use this in this problem right this second, but you could also write that, divide both of those terms by 3. So you would have like x over 3 plus 15 over 3, which if I was trying to write that to graph it, I might call that 1/3 x. That would be your slope plus 5. It's just sometimes the line might be presented to you in that format. So if the x is on the top and you got a number on the bottom, it's just trying to be linear there. I'm going to use the actual fraction when I do this composition to show you guys what that looks like visually though. Okay, now if you compose, and we're just going to do both, so I'll just draw a line down the middle here. So this one says put the inverse into the function. Okay, so the inverse is this guy right here. And everywhere I see an x in the original function, which is just the 3x minus 15, I'm going to replace it with that lovely fraction. And this was no big deal. It looks bad, but it's not. All right, so instead of 3x, I'm going to write 3. And then I've got this fraction in parentheses here. And then minus 15 on the outside. So what I'm doing here, here's me plugging the entire inverse in place of x. Okay, now, I don't know if you guys will notice this, and people will do this. They will like distribute the 3. Don't do that. Okay, do you see how there's a 3 on the outside and a 3 underneath this? This would be like a 3 over 1, okay? This actually just cancels that out. You don't have to distribute it in there. If you've got this number on the outside that you're multiplying and you're dividing by the same number, they literally just cancel each other out. All you would have left with that would be x plus 15, which was on the top. And then I had this minus 15 on the outside. And then if you combine the like terms, you have a positive 15 and a negative 15. And that cancels each other out and just becomes x. And that's what we're trying to show. Now I'm going to reverse this. So to show their inverses, you have to show that both of these algebraically simplify to be x. So to reverse this, I'm going to now compose the inverse with the original function. So that means I'm going to take the original function they wrote here in the directions, and everywhere I see an x in the inverse, I'm going to replace it. Okay, so the inverse has a fraction, and on the top it has x plus 15. In place of the x, I'm going to put the 3x minus 15, and then I had a plus 15 up there also on the top. So this is me replacing the x with the original function. Okay, now if you guys look at that fraction, you can simplify the top of that fraction a little bit, right? So the 15 and the negative 15, they would just cancel each other out. So on the top, I would just have 3x over 3. And then this is just a little review, just division here. The 3's cancel out, and this simplifies to be x. So the algebra looks a little bit different. It's similar, but we're composing one function with the other, and then we're flipping it around. So the algebra does look a little bit different, but you're trying to show that both of those simplify to be x. So the inverse and the original, they literally just cancel each other out. Does anybody have a question at the moment? Okay, so those are both lines. Let me show you these inverses. In example B, I've got a quadratic, that's the squared, so a parabola, and then I've got a square root. So square root and squared cancel each other out. Square root and squared are inverses of each other. So my original, this is going to be a parabola. So it's just x minus 3 squared plus 9. And my inverse is going to be the square root, which is square root x minus 9 all under the square root, and then a plus 3 on the outside. Okay, so to start this, I'm going to do the function with the inverse plugged in. So we're going to take this whole expression here, and this is going to look really complicated, but I'm going to plug that whole thing in for x in the original function. So the original function, I start off with parentheses, and then it has the x. So I'm going to put this x minus 9 under my square root, plus 3 is outside of that, and then I have a minus 3, and that whole thing is squared, and a plus 9 is on the outside. So here is where I put that inverse, that's where I put that in place of x, and then it had the minus 3, the squared, the plus 9. If you guys notice, right in here, in the parentheses, the positive 3 on the outside of that radical and the negative 3 that was also there, those just cancel out. So I get, in the parentheses, x minus 9 all under a square root, that's squared, and plus 9. What would that first term become? Like, what happens if I have, I'm taking, this whole thing's under a square root and I'm squaring that? What's that going to do? Yeah, these cancel each other out, but you still have the x minus 9. So the square root and the squared cancel each other out, but I would still have what was under the square root, which was the x minus 9. And then we had the plus 9 on the outside, and this is exactly what we want. Go ahead. This one here? Okay, so this function was x minus 3, right? And I replaced x with this kind of complicated square root. So this whole thing is where the x, yeah, does that make sense? I tried to kind of highlight, so that's where the x was, and so the minus 3 was from right there. I know these can be really tricky, especially if they're kind of long. Does anybody else have any question? Okay, now, so this is what we want though, because then we get this negative 9, positive 9, those cancel each other out, and we're just left with x, which is what we were trying to show, that if we put the inverse into the original function, it will just simplify to be x. That's an indication that they're inverses, but you have to prove it both ways. Okay, so the other direction, now I'm going to take the original function and plug it in everywhere I see an x in the inverse. So the inverse starts with the square root, and then I have the x. And in place of the x, I'm going to write x minus 3 squared plus 9. And then I have a minus 9 under the square root. So this part is just, I'm putting that whole expression in place of x. So that's kind of long there. But that whole thing goes in for x. And then we had a minus 9 under the square root with the x. And then I have this plus 3 on the outside. Okay, now if you look under the square root, you have a plus 9 and a minus 9, so those are going to cancel out. So that first term would just simplify to be x minus 3 squared under a square root. And then I have a plus 3 on the outside. Okay, now it's similar to the last question, but it's actually reversed. The last question we had, I had a square root that was being squared. Here, I have a square root of something that's being squared. So it's reversed, but same thing, square root and squared cancel each other out. So this just becomes x minus 3. And then you have this plus 3 on the outside. And the minus 3 and the plus 3 are going to cancel each other out. And you're left with x, which is what you're trying to show. Does anybody have a question? Okay, now this next one is kind of, one way is a little bit makes more sense than the other. It's kind of tricky though. So if you have an exponential, its inverse is a log. And so that's what I've got in the example down here at the bottom of the page. Okay, so the original I'm going to use is 5 to the x minus 2. And the inverse for this one, it's a little bit different colors, is going to be log base 5 of x plus 2. Okay, this one's going to look a little bit weirder than the other one. So I'm going to plug this whole thing in for x here. So I'm plugging the inverse into the original. So we have 5, and in place of x, we're going to have the log base 5 of x plus 2. And then, so that's me placing that, you don't need parentheses, that's me placing that in for the x. And then I had a minus 2 that was also in that exponent. Sorry, this is really out of focus right now. I'm going to use a different pen. Okay, now, what will happen in that exponent, what I'm going to do right away, I have a plus 2 and a minus 2, and I'm just going to cancel that out. So I have 5 to the log base 5 of x here. And this is weird to show algebraically. So what I'm actually going to do, I'm just going to put, and you can put any variable you want. I'm just going to put a variable on the other side so I can kind of have a place to do this. Or no, actually, you know what? See if you guys remember this from first, or a little earlier in the semester. No. Okay, let me just do this. I'm going to put a y over here. I'm going to convert this. This is an exponential, and I know it has a log in it, but I'm going to convert it to a log. All right, to do that, I'm going to slide this 5 over here. The base of my exponent is going to become the base of a log. So I'm going to write that as log base 5 of y. And then equals, that brings that exponent down on the level with the rest of the question. Log base 5 of x. I'm really just using that y as a placeholder. We're trying to show that this becomes x. And if you guys remember, if these are the same with the same base, then this would just end up being y equals x, which is what we're just trying to show, that simplifies down to be an x. To convert that to a log is basically the fastest way I could show you that. If you look at this, I just know this, if you have a base of your exponent and it's the log with the same number, those just cancel each other out. It's a little more obvious when I do the reverse. So let me reverse this. This one's easier. Except I think this is also going to review something we did first semester that I want you guys to see. Okay, so I'm going to plug the function into the inverse to compose this one. And we're going to show that this is equal to x. So I would have the log base 5 of 5 to the x minus 2 power. And then I have this plus 2 to the side. Okay, 2 properties I'm going to review from our exponentials and logs unit to do this. Okay, do you guys see, I don't know if you'll remember this property, but I'm going to use this here. If I have an exponent, and I'm taking the log of something, if you have an exponent, there's a rule called the power rule, and I can bring that down in front of the log, and I am going to do that here. So I'm going to take that x minus 2 and bring that down in front. Okay, so that's just using the power rule. If you have an exponent, you can bring it down in front of the log. Okay, now, here's the other thing I want to review with you real quick. Does anybody remember if I have the log base 5 of 5, if I wanted to evaluate that, do you remember if your base and what you're taking the log of are the same? Do you remember what that's equal to? If you don't, I could just do it real quick. If you don't remember, okay, let me do it real quick. So if I wanted to evaluate this, or you could do it on your calculator too, If I got rid of the log, I'm going to just change this to an exponential really quick. This would say 5 equals 5 to the x. What would x have to be to make that true? What would my exponent have to be? Just 1, right? So x is 1. So this log base 5 of 5, that is just equal to 1. All right, so let me come back over here. So really what I have is x minus 2 times 1 plus 2. Well, if I do x minus 2 times 1, that's just x minus 2, and I had this plus 2. And so those 2's are going to cancel. One's negative, one's positive, and that will give you the x. But if you have a log, it has a subscript, is the same thing as what you're taking the log of, then that's going to end up being 1. That one's probably the hardest. Is anybody having a question about that one? Okay. Now, I'm not going to do example 3. We're just going to finish up with example 2, and then I'm going to cut some problems off you guys' homework here today. So we're just going to finish this one up here. But I'm going to actually have you do some composition with numbers, and these are inverses of each other. So my original function, I'm going to give you 3x minus 15, and the inverse, these are inverses of each other. So I'm going to show you what happens if we plug a number in instead of plugging one function into the other. All right, so this says f inverse composed with f of 12, so not multiplication. If you like the other notation better, this would be f inverse of f of 12. Okay, so that means we're going to start and we're going to plug 12 in to the f of x function. So f of 12. So that one's this, 3x minus 15. So I'm going to do 3 times 12. Everywhere I see an x, I'm just going to replace it with the number they gave me. So just going to put in 12 for x there. What is that? 36 minus 15. So this would be 21. Okay, when you work with composition, it tends to be 2 problems in one. So once I get that, what I want to do is I want to take that, let me find a different color here, and I'm going to plug that, replace f of 12 with what it was equal to. So it's 21. So then we're going to do f inverse of 21. Okay, f inverse is this other equation they gave us over here, this 1/3 x plus 5. So everywhere I see an x, we're just going to replace it with a 21. And so 1/3 of 21 is just like 21 divided by 3. So that's 7 plus 5. And this will give us our final answer, which is going to be 12. Anybody have any questions? Does anybody notice anything about that? Exactly. Okay, exactly. Like, so look. So I used the function first and then I used the inverse, but what I told you guys to plug in is exactly what I got as my answer. Okay, so let me reverse this. Now this is a different number, but this has you putting the inverse first. So if you like the other notation, this would be f of f inverse of negative 24. What that just means, we're going to plug negative 24 into the inverse first. So the inverse of negative 24, we're going to do 1/3 times negative 24 plus 5. So 1/3 of negative 24 is like negative 24 divided by 3. This is just negative 8 plus 5. So you're going to get negative 3. And then remember, this becomes 2 problems in one, so I'm composing these. So then I take what I get here, just like a little substitution. I'm going to do now f, the original function, of negative 3. So that would be 3 times negative 3 minus 15, which you're going to get there negative 9 minus 15, which is negative 24. And then again, you guys can see I got back exactly what I asked you to plug in. So it didn't matter if the function went first or the inverse went first. Either order, they should cancel each other out and just give you back what you plugged in. Okay, now I'm going to do one more with you just to show you this always works. It even works if you do this with variables. So now this one's probably the trickiest, but this has a variable, so I'm not going to get a number. If I plug variables in, I should get variables out. So this is the function composed with its inverse of 3a. Okay, now I promise this is just going to be a little algebra, it's not bad. So if I plug into the inverse 3a, so the inverse was this 1/3 x plus 5. So everywhere I see an x, I'm just going to replace it with that expression 3a and just see if I can simplify anything. Now, I can't take 1/3 times 3. What is 1/3 times 3? Just 1, right? They're reciprocals, so these guys cancel each other out. That first term would just become a, and then I have this plus 5. I can't go any farther with that, so then if I'm doing the composition, I know this is a little tricky, we're just going to plug this expression into the f of x function now. All right, so I'm going to do f with a plus 5 plugged in. So everywhere you see an x, we're just going to replace it with that whole expression. So in that function, we had 3, and then I'm going to have a plus 5, and then I had a minus 15 on the outside. All right, so if I do the algebra here, this would be 3a, little distributive property, plus 15, but then I had this minus 15 on the outside, so that's going to cancel with the positive 15, and we're just going to get 3a. And again, what I asked you to plug in, that's just going to be the actual answer. And that happens anytime you compose a function with its inverse. If you know their inverses, if I give you a number and say plug this in, tell me what the answer is, you wouldn't even have to do any of this work if you remember this. They should just cancel each other out, and it should just give you whatever that number is. So this just says in general. So if you compose a function with its inverse, or I'm going to write vice versa, because if I switch that, like if I do the inverse composed with the function, you saw it works both ways. If you compose those two things together, they cancel out, and they just give you whatever you plugged in. I could literally give you, say this is a function, this is its inverse, and put a little picture of a dolphin. And you could just know that it doesn't matter what the functions are. If they're inverses, the answer would be whatever's in the parentheses that I asked you to plug in. All right, so when you get to questions like this on the homework, if you could defend that to me, if you could remember that, you could just say, like, if I saw that, I would just write 12. I would not have gone through all that work. I was just trying to show you guys it worked. If I saw this problem, I would just write negative 24. If I saw this problem, I would just write 3a. So if you can remember that, then you can just write that down. If you don't, if you go ahead and do the work, it'll still give you the same answer. Is anybody having a question? Yeah. No, like if I give you this and you just write the number, I would give you full credit for that. If you wanted to write the work out, you could, but if you can remember that a function composed with its inverse, they cancel each other out, just go ahead and write that. We just proved it on the front. We showed that whether we did it with the function and its inverse or the inverse and the function, it just simplified to be x. Okay, and I'm just don't worry about this. This is a little bit of review from what we were doing yesterday, so just skip this at the bottom. And then when you guys are looking at the, I thought I had a homework paper up here. I think it's the last 3 questions on the homework. Let me see if I can find one. Here we go. You could do them if you want to for some extra practice, but if you want, this is on the homework assignment. If you want to just skip like 8, 9, and 10, that just goes with that last example. Don't worry about those unless you want some extra practice. If you want, you can do them. If not, that's fine too. So just 1 through 7 for tomorrow. And if you get to like 5, 6, and 7, you don't have to write out a bunch of work for that. If you want to prove it to yourself, you can actually plug it into the functions. It might go kind of quickly. But if you just want to remember a function that's inverse composed together, give you back what you had, that's totally fine.